Thank you very much for having me today, and I'll give 2 lectures. The first one will be related mainly to multilevel Monte Carlo, and the second one we will touch upon multi-index versions of the things that I'm going to say today, but not in an adaptive fashion, as we will see. Okay, so first goal then to discuss a little bit of adaptivity within multilevel Monte Carlo. Let's see how this goes. So the plan is as follows. Well, these are some pictures from the place I come. This is KAUST actually. It's King Abdullah University of Science and Technology. Some of the students are here today. And let's see, this is the plan. So most of you are very well acquainted with Monte Carlo and possibly multilevel Monte Carlo as well. So I will recap a little bit just to set up the notation at the beginning, right? So we both speak the same language, and then we go into different versions of adaptivity. As you will see, there are many ideas for adaptive approximations in multilevel Monte Carlo that we can see. And for that reason also, I will touch upon different models. I mean, one of them will be computations with random PDEs, that is PDEs that have random coefficients. The second one will be diffusions. These are Stochastic Differential Equations. And the third one will be pure jump processes, say, Stochastic Reaction Networks, right, whose trajectories are piecewise constant. Okay, so I think this will motivate a little bit different ideas that we will have in this. And finally, we will discuss a little bit of continuation multilevel and optimal hierarchies. Hopefully, if the time allows, I will also discuss optimal stopping with non-asymptotic rules within Monte Carlo. So I'll try to really be adaptive in this process. So let's begin with our first example. This is a linear elliptic PDE that is very popular in the context of random PDEs as a model case. So here, the coefficients A and F are random processes, I mean stochastic random fields, and mainly we'll concentrate on the effect of A because A is with the 2, right? The one that acts non-linearly on the solution U. And out of the solution U, we are interested in computing a statistic which is real valued. Again, as an example in this lecture, I'm going to go through the computation of the expected value of a functional of the solution, here depicted by psi of U. Psi could be linear or nonlinear. We have some restrictions on smoothness on psi, but for the moment, think of a linear functional that is deterministic acting on U. Again, this is not the only thing that you can compute with multilevel Monte Carlo, but this is the one that we will be focusing mostly through the lectures. All right, so the goal is set. We want to compute this expectation. Now, this expectation involves the solution of a differential equation. Seldom do we have the actual exact solution of U at our disposal. So instead of U, we're going to approximate it by UH, say, where UH comes through a discretization of this equation. In this case, of course, it will be only space discretization, but in general, you may have time as well, or even other parameters. So think that you have prescribed the use of your favorite method. In this context, could be finite elements, finite difference, finite volumes, or whatever. And that discretization is indexed by the parameter H. All right? So H will govern in 2 aspects the solution. One will be the approximation characteristic of UH to U, but at the same time, the cost of evaluating UH, with the assumption, of course, of consistency, meaning that when H goes to 0, UH converges in the proper space to U, and at the same time, the cost of evaluating UH goes to infinity, right? Otherwise, we will let H go to 0 and get an exact solution. Now, since we were interested in this functional, actually, which is a real value random variable, we will approximate, I mean, in the notation, denote the approximation by GH, where now H is the discretization parameter, all right? So that's hopefully a natural notation. Let's go through the error then. The difference between what we would like to compute, which is the expected value of G, minus what we actually compute, which is a sample average based on IID samples out of the inexact quantity, which is GH and not G, right, can be split upon two main sources, right? One, again, the trick is to somehow subtract the expected value of this approximate quantity to split the difference between this and this into two things, right? One that we call the bias error, the other is the statistical error. And for the bias error, we have essentially an estimate of this kind, which is coming directly essentially from the deterministic analysis, right, pointwise, and then integrated upon this expectation. So essentially what we have is that if your method has order W here with respect to H, which is the discretization parameter, well, essentially the constant that comes from the deterministic analysis will be random, of course, because it will be depending on A and F. But once you take the expected value, you get the average of such a constant, which is no longer stochastic, it's just a deterministic constant, all right? So this analysis holds as long as there are no changes of order with respect to the randomness in the problem, which is a reasonable assumption. But if that happens, actually this will not be the correct way to draw things. But again, this is an introductory way to explain how this works. So let's again consider that this W doesn't change with respect to omega, and therefore we just get a constant here times H to the W. Okay, so this is more or less a standard discretization error. Second term is the standard statistical error, right? And this error essentially is mainly governed by the number of samples M, and I say mainly because the random variable that you're actually sampling depends on H, right? So this is an unbiased error, correct? Because we take expected value here and then sample of the same random variable in an ID fashion. We only need to control its variance, right? And that is motivated by the central limit theorem. Essentially, properly scaled, right? This will be approximated by a normal distributed random variable, and this allows to write then later the constraint of having this error smaller than a certain quantity in probability, as a constraint in the variance, right? So as we can see, again, we have two contributions here, one coming from H, the other coming from M, and as long as the problem is a reasonable well-posed problem and there's nothing strange, this variance is uniformly bounded with respect to H, right? And therefore they claim that M is essentially the quantity that governs the statistical error. Okay. Again, if the problem has a singularity of some kind, maybe this is not completely true. But I mean, again, in the examples that we're going to visit, this variance is going to be bounded uniformly with respect to H. Okay. So two sources. One is governed entirely by H and converges algebraically with respect to H. The W here is determined by the numerical method that you use and the regularity of the problem that you're solving. And this M is very robustly coming into this analysis, right? We only need to ensure that this variance is bounded, essentially. So now that we have the two main errors identified, we try to see what is the corresponding complexity, which is the computational work that is needed to achieve a certain accuracy with Monte Carlo in this context for a prescribed confidence level, okay? And to do that, essentially what you do is to minimize the work subject to the total error constraint, okay? So the total error constraint, again, in probability, because this was essentially analyzed in probability, is the sum of the bias plus the statistical error. The bias was governed by this, the statistical error is governed by that. And the total work, naturally, is what? Is a product between the number of samples that you have to solve for, right, times the expected cost per sample, okay? And again, this is an example, right? And the example that we have illustrated is a linear elliptic differential equation, right? And in that case, what we have to do is to solve a linear system every time we need to create a new sample of the random variable. So if V is the dimensionality of the space that you're solving, right? I mean, it could be 3D, for example, 2D, 1D. Then H to the minus D, if H is a discretization parameter, is essentially the number of degrees of freedom that you have in your discretization. So H to the minus D is the degrees of freedom, and then to the power gamma is essentially the cost that one incurs by solving the system. Okay, so gamma equals 1 will be an optimal solver, and gamma equals 3 will be the Gaussian elimination. Okay, so gamma can range between 1 and 3, and of course h to the minus d is the number of degrees of freedom in your system. Is that clear? Okay. So this adapts to, again, to the type of solver. If you use one type of solver or another, this gamma may change. Okay. Let's see what else is to be said. Yes. Okay. So I mentioned the following. I said that this cost was understood in the mean sense. And why do I say that? Well, if actually you have an iterative solver, right? And you know, the spectrum of the operator that you're solving with is random, right? Because the A, this diffusivity coefficient, was random itself. The number of iterations may depend on the realization, right? Okay, so what you're really interested in is the mean cost, not just you know, the cost. I mean, the mean cost. The mean cost will be representative, and there will be variations with respect to each of the realizations. Is that clear? Okay. Now, if you use a direct solver, this will not be the case. But okay, I just want to emphasize a little bit on that. Now, if you actually do the minimization of this bound and subject to this constraint, you get this classical cost with respect to the tolerance that you're imposing. Okay. In the context of the central limit theorem, the confidence level is only acting on the C2, so it really plays no role in this constant. It's just, I mean, in this exponent, it's just acting on the constant, and that's why you don't see it. But again, everything now depends on the accuracy you want to achieve, and can be split into two contributions. One that is told to the -2, and the other is told to the minus d gamma divided by w. Now, the first part, told to the -2, is the classical cost in terms of number of samples of a Monte Carlo method, right? This is essentially what is needed to make this less than tall, right? So that will be the cost that one will have to pay if each sample costs me over 1. The second part of the cost is coming from the fact that I need to make h sufficiently small so the bias constraint is satisfied, meaning that this term is actually less than tall. Okay? So essentially what you see here is the number of samples times the cost per sample, which is essentially what you were seeing here as well. Okay? Now, what multilevel Monte Carlo tries to do is to go beyond this bound. So what we will improve somehow is this part, and this will still be a barrier that we will not be able to cross, at least with Monte Carlo methods. So just to give the notation again for multilevel Monte Carlo, let's recall this construction of Heinrich and Giles. Let's take a constant beta for subdivision. For all purposes, think of beta equals 2 for the moment. Okay. So what we say is the following: instead of just taking a single h that was meant to satisfy the bias constraint, what we're going to do now is to take a number of such h's. In principle, if you come from analysis, from numerical analysis, this is a natural way to proceed, because every time you are actually trying to solve a differential equation, you try with a certain mesh. If you're not happy, you subdivide it, right, and you test the stopping criterion. And if you're not happy, you subdivide again until you meet the stopping criterion. Normally, what you do is that once you get to that level that you accept the error to be smaller than your prescribed accuracy, you throw all the other things, right? You don't care essentially, and you just work with the last accepted guy. Here, on the contrary, you're going to keep those for a certain purpose, and the certain purpose is to produce an effective control variate, right? So what one is doing here, again, let's go through the definitions first, is to introduce these deltas operators, right, that are differences between consecutive approximations. So essentially this, remember, is the functional evaluated using a mesh of size HL, and this is the functional using a mesh of size HL minus 1. This is the difference between two random variables, and we are assuming, of course, that they are not independent, right? They're going to be sampled according to the same omega. That's fundamental in this construction, because that is what will make this difference actually go to 0, essentially, when little l here goes to infinity. That, again, comes from consistency. In L2, this is what we're going to mainly need for this to be working fine. So let's go again to the construction. The construction of these HLs is done via a geometric discretization, meaning that you start with a given mesh. If you're not happy, subdivide it by 2. If you're not happy, subdivide by 2 again, by 2, and so forth. Okay? That creates this HL based on H0 divided by, say, beta to the minus L with beta equals 2. Is that clear? Okay, so now that these deltas have been defined, then one rewrites. Remember, this was the guy that we were trying to use as an approximation to this one, so that the bias between these two was less than tall. Now, this is somehow the random variable that one is going to apply control variance to, and before doing so, one rewrites this expectation as this other sum. Okay, so this is an exact representation, and the sum is running over all levels of approximation from 0 to the level L capital that satisfies the bias constraint. Yes? Now, instead of using Monte Carlo here, one instead uses Monte Carlo independently for each of the terms coming into the sum. All right? So, and that's sort of a scary proposition, because the first time you see here, this is saying at the beginning I only had one expectation to compute. Now I have L capital plus 1. How is it going to work? Well, okay, before we look into that, let's see how this looks. And as you see, this, which is actually the estimator for multilevel Monte Carlo, looks precisely like the sum, right, of L capital plus 1 Monte Carlo estimators, where each of them now is sampling something different. Each of them is sampling these deltas. And of course, remember that for L equals 0, actually, this is not a difference, it's just G evaluated on the coarsest approximation. Okay, so you can think of this as, G is H0, right, if you think of hierarchical approximation, and then the other things are just corrections, right, that are being added to the coarsest level. Now that we have this, how do we motivate, at least first intuitively, why is this going to work better than the original Monte Carlo approach? Well, let's see, the bias is not going to be changed. We said, essentially, if this L is chosen so that this bias is less than tall, what we are rewriting essentially is this quantity. So if you're going to actually improve this sampling, is because we're going to pay less in the samples, essentially. The difference will not come from the bias. Yes, please.
So how do we choose M for each level?
Oh, this is coming.
Okay.
Yeah, this is coming. This is coming, don't worry. Piano, piano. Okay. Now, the variance here is the variance of Monte Carlo, right? So what did we say that the constraint, the statistical constraint looked like? Well, essentially, thanks to the construction based on independent samples, the variance of this estimator is just 1 over ML capital of the variance of this GL capital. Now, you think that the GL capital is more or less close to G, so more or less you can expect that this looks like the variance of G divided by ML, right? So this is essentially saying that in the deepest level of approximation, L capital, the one that satisfies the bias constraint, you need to use 10 to the minus 2 samples, right? And that is what you expect from Monte Carlo. If you, on the contrary, use multilevel Monte Carlo, right, the variance for the estimator, again, by the construction of independence, not only between the samples that we use on each level, but among levels, right? We get a sum of variances across levels. The first variance, the one that is coming from the level 0, actually, looks very much like this term, right? This is not a difference. This is not a difference as well. But the other terms are actually 1 over m, right, times variance of differences. And what's the point here? Well, remember, as little l gets larger and larger, we hope to have convergence, okay, just by consistency. Now, in which sense we expect to have convergence? In this setting, what is most useful is to consider not only you have convergence in the mean, but also in L2, which means that these variances of differences are going to 0, right? This is where multilevel Monte Carlo becomes effective. And if they actually become very, very small, it means that for really deep levels, when L is large, right, each sample costs me a lot, but the variance is correspondingly small. So the number m that I will have to use is really small. And this is where you get real advantages, because you're sampling much less in the most costly levels. All right? Now, you have to check some conditions usually to make sure that the choice of the level 0, say, is sound, but again, the whole thing can be put in terms of these inequalities that, again, indicate that L2 is very relevant in the choice of the multi-level parameters. So far, so good? Any questions?
You said there was going to be correlation between the different levels.
No, there's not, actually. No, they are constructed totally independent. Okay?
So
that's important, yes. From the independence in the construction, you get immediately this sum. Okay? Otherwise, you will have extra terms. All right? It's not that it's impossible to do that, but the construction here is done on independence assumptions. Okay, so cartoon type of approximation, essentially, we are somehow moving samples from sort of deep refined levels that are costly into levels that are cheaper and less refined. Okay? Okay, so if you want to go beyond that intuition, you need some assumptions, right? And these assumptions may or may not hold in your problem. You have to verify that they are satisfied, and sometimes you may have precisely this kind of convergence and some other type, I mean, depending on what problem is had. So here we are again going to concentrate on this algebraic type of convergence with respect to H. Remember, H was a parameter of discretization. You can think of delta X, delta Z, delta Y in your linear elliptic PDE. And we were assuming that the HL was essentially H0 times beta to the minus L, right? A geometric subdivision. So this first equation here is nothing different from what I wrote before, right? It means that the mean, the error in the mean is H to the W, essentially. You see? So nothing is different. It's just a rewriting of what we had before. Now, again, this W, which is the exponent of the weak convergence, depends on the assumptions on your problem and the numerical discretization that you're using, and has to be found for each problem, right? The variance, assumption, again, is indicating some kind of error rate, but this error now is measured in L2, and instead of taking the difference between G and GL, now we are taking, remember, the difference between GL and GL minus 1 when we put it inside of the difference. And we have a strong rate of convergence that is S, which is not going to be W, right, in general. So for the last one, we have the cost, the mean cost of evaluating a difference on the level L, right? So this is delta GL. And this again entails the cost of evaluating GL and GL minus 1 because we're going to take the difference. Usually one assumes that GL is the one that dominates, so this goes like that. And this is nothing from what we said before, again, because before we said that the cost was H to the minus D gamma. And again, this is the same thing, just rewritten in terms of this beta and this L. I emphasize again that the constants C, W, and S also depend on the problem and have to be found. And remember, gamma may depend also on the solver that you use, not just on the problem and the discretization. So if you change the solver, gamma will change even though you keep the rest of the things constant. As an example, for a smooth linear PDE of the type, linear type that we discussed today, if you use multilinear piecewise continuous finite elements, we will have 2W equals S equals 4, and of course, depending on the solver you use, gamma ranging from 1 to 3. Okay? So what's the total work? And here we start getting close to your question about the M's. The total work will be found upon in the same way as we did with Monte Carlo. We have L capital plus 1 levels. On each level, we have to use ML samples, and the cost per sample, right, is the work of delta GL in expected sense. So what do we do? Well, remember, we have to find ML. So if you fix L, essentially you can write an optimization problem, and I'm going to go into that a little bit more when I go into multi-index Monte Carlo, but we can just say it again. I mean, remember, if you fix L, the bias constraint is not going to be important, and what you want to minimize is minimize with respect to the MLs, right? From L equals 0 to L capital, what? The total work, right? And this is the sum from L equals 0. I hope it is possible to see this, right? There's no reflection or anything like that. So L capital, ML, and this work, delta GL. And then, of course, there's a constraint, right? The constraint is the statistical constraint, right? And the statistical constraint, again, is the variance being less than tall square. So what is the variance? Again, is just 1 over M0, say, variance delta, actually G0, just I write it differently, plus the sum from L equals 1 to L capital of the variance delta GL divided by ML. And this is less than tall square. Of course, there's a constant here in between, but I'm not writing it. The constant comes from the confidence level that you want to impose, say. Okay, so the control variables here are ML, L capital plus 1, right? And here you see how they act. So you can just write a Lagrange relaxation, and you realize that you can find these MLs, and MLs actually are going to be, at least if you make a real value relaxation first, this will be tall to the minus 2, and then there's a constant here that is coming out of the levels, and this essentially is the variance of delta GL, I think. You may correct me if I'm doing this wrong, and then this is the cost essentially. And this is square root here, if I'm not mistaken. Okay, so you can first, write this Lagrange relaxation, solve it, and then say round it above. I mean, take the ceiling of this number to make sure that everything goes well. Okay, and that from there you get to that formula, essentially assuming that you have to assume that the cost is not trivial, essentially, that you're not getting less than one realization per level. But okay, that is a technical assumption. You can stay with this for the moment. So what do you see from here? You see that after you substitute the optimal number of samples, the cost only depends on L capital, right? Because these are problem, say, and discretization-based constants. Okay, so once you give the discretization method and the problem, of course, this work L and the variance L essentially are given. Maybe you don't know them precisely a priori, but they're given. So, and this is a sum of positive terms. So, first thing that you observe is that when the tolerance goes to 0, L has to go to infinity, right? Is it clear why? You have to satisfy the bias constraint, right? So the bias constraint essentially was h to the w less than tall, and L is coupled directly with this h to the w. So L essentially goes to infinity like a logarithm of tall, absolute value. Say that's the ballpark. You may have log terms on top of that, but it really is log tall. So this is going to infinity as tall goes to 0. So this sum can only do two things: either stay bounded as tall goes to 0, or diverge. If it is divergent, it's because this work is somehow growing faster than what the variance is being able to converge, right? But if it is actually finite, which is essentially the case where this variance is dominating the work somehow, we have a very interesting case that is sort of not intuitive the first time you see it as well, is the fact that you get a cost that is essentially O of tall to the minus 2. And if you remember Monte Carlo, when we discussed it first, tall to the minus 2 with the optimal cost with Monte Carlo, when each of the samples, essentially in the mean, cost me O1. So essentially this means that you don't feel the cost of discretization even though you're refining the levels, right, infinitely much as tall goes to 0. Is that okay? In principle, not, right? So somehow it means that even though we still have to sample of those at the level L capital, we only sample so little samples so that cost really does not influence the rest of the costs that come from the other levels. Okay, because we still have to sample in that level. That is clear, right? Okay, so now that you see what is coming, let's see the result with these assumptions in mind. So L capital, as I told you, is determined by the bias constraint and essentially is linked to toll by a log factor, right? Where the log essentially comes connected with the weak rate of convergence and the logarithm of the subdivision multiplicative constant, beta. And remember, the samples ML are chosen optimally like we discussed before, just by solving that Lagrangian relaxation problem. And after substitution, essentially you get this fantastic case, tau to the -2, where S is larger than d gamma, right? So essentially both the work and the variance are behaving with respect to L in an exponential fashion, right? So the work is growing with the d gamma rate, and the variance is decreasing with the S rate. So as long as S is larger than d gamma, this sum is convergent. And this is what explains the first result. The second is a limit case where essentially they outmaneuver each other. So essentially they balance each other. You get something that is constant here. So the total result here is L on this sum, L times a constant, and then you get L squared. And L was log toll. So that explains the second line here. And in the last one, well, the work is growing faster than the variance is converging, and instead of getting something that is convergent, you get some algebraic deterioration. But still, this algebraic deterioration is better than what you will get with Monte Carlo. So you're decreasing from d gamma here in the explosion to d gamma minus S. Okay? So you're still exploiting a little bit of the strong convergence, I mean the convergence in L2 that one assumed. So, okay. So far for the introduction with the uniform methods. Now the question that we want to more or less touch upon is how to extend this multi-level Monte Carlo into non-uniform adaptive discretization settings and whether it's worth it. Okay? And there are several ideas to introduce non-uniform discretizations or stochastic levels, if you wish. So let's begin with the okay, well, this is, I put just to include in the slides, and I already gave up trying because, I mean, the pages are not enough actually to describe so many things, and I rather just direct people to look into Mike's humongous effort to keep up with the growth of the community, and this is actually where you get the best references in the list of references in the area, so I'm not going to stop too much into that. So let's go to adaptivity then. And in this context, again, we were trying to approximate the expected value of an output quantity. In this case, I'm switching the example. I'm going to stochastic differential equations, Ito differential equations. So in this setting, each of the paths evolved in finite dimensions with respect to time, right, until you get to a final value, and then in that final value, you may evaluate the function g here that comes in this example like a put option in finance, and then you have to integrate this g versus the PDF of the final time. Okay, so you can do this with Monte Carlo just by sampling many paths and again averaging as we discussed before. So here are some references again. I'm not going to stop, and I'm going directly into the problem formulation. The problem formulation is an SE. This SE, if you have not seen it before, it's not a problem because you can think of this discretization via Euler-Maruyama. That is coming just in a second. So x is something that is finite dimensional now. It's not a function as in the first example. It evolves in RD. And g is a given function so that our goal is to compute the expected value of g of xt capital. So evaluation at final time of the solution of an SE. Again, we are given an accuracy constraint toll and a prescribed confidence level. and everything is driven by a k-dimensional linear process. All right, this has plenty of applications that I will not stop upon, and okay, what we're going to go is through this Adaptive Multilevel Monte Carlo, and actually see that there's several versions now of adaptivity. The first one we did was with respect to the weak error, but later we did something that controls the strong error, and yeah, let's go into that later. So first, the discretization algorithm. This is just Euler-Maruyama, so if you have not seen SEs before, this is a new term that comes in. So remember, it's coming through this. If you just think of the first part, it's just forward Euler, right? Based on this function, the drift function A. And the second is just the same type of discretization. You see, you have to evaluate B on the left point, essentially the current point, x bar, but you multiply times these random variables. These random variables are normal distributed with mean 0, and the variance is just the delta t that you're taking. Okay, so the delta t does not need to be uniform at all, right? But yeah, and again, weakly you can just scale them to normal 0, 1 random variables. And the Monte Carlo estimator looks exactly as we discussed before. It's an average of IID samples, but the IID samples are not from the exact process, but from the solution coming out from this forward Euler. Forward Euler, of course, is not the only discretization that one can do in this context, but it's the one that I'm going to exemplify. Okay, so as we discussed before, this can be split into tolerance for time discretization and tolerance for statistical error. And this is a particular case of what we discussed before. The cost per sample here is essentially proportional to the number of time steps. The number of time steps essentially is proportional to 1 over tol, that is coming from the weak convergence rate 1 of Euler, which is the same as Euler-Maruyama in this setting. And this brings us to the complexity tol to the -3 for Monte Carlo. Okay? Okay, and now you want to introduce adaptivity. So what is adaptivity in this context? In this context, adaptivity means the ability to choose the time steps non-uniformly. And this non-uniformly can depend also on omega. So the time steps such that t0 is 0 and the final time step is t capital are not going to be equally spaced, and they may adapt to omega because the dynamics of the solution may depend on omega in a dramatic way, maybe. So in this context then we will create realizations that depend on x bar, I mean here denoted by x bar, and depend on these meshes delta t of omega. So again, why do we do this? Well, sometimes there are non-smoothness on A or B that ask that deteriorate the usual behavior of the uniform method, so ask essentially for adaptivity in a natural way. And what do we need to be able to produce such delta t's? Well, you need, at least with our approach, you need to rewrite the weak error in this other way. Essentially, you need to introduce an error density, which is a function rho w that does essentially not depend on delta t, so that the error, the weak error, can be split essentially in contributions that are coming out of each of the different discretization steps. You see here, if you discretize over the time steps, this is a sum over time steps of essentially delta t n square times rho w. Okay. Now the fact that delta t here is inside of the expectation is allowing for the choice of stochastic time steps, okay? Because rho w may still vary dramatically with respect to omega. That's the point. If this rho w will not be varying dramatically with respect to omega, then it's cheaper actually to take a non-uniform but deterministic discretization with respect to delta t. Is that clear? There's an overhead to do this fully stochastically, so whenever possible you avoid that. Now, the funny thing is that in this context, there's not only a weak density, but there's also a strong density. You can actually make an approximation, and you see here the power is 1, but here the power is 2. You can actually write the L2 error here in the same fashion for Euler, where now this rho s is not exactly this rho w. It is still something that you can approximate with computable quantities, and it's able to distribute the strong error across the different intervals that come into discretization. In principle, this is not obvious because when you square this, you may get a lot of cross terms, right? So to be able to tell that actually the diagonal terms are the one dominant, this needs some understanding. Okay, but what is the whole point now is that once you actually produce these error densities, you can produce single-level adaptive algorithms. So single-level adaptive algorithms will try to find these time steps so that, say, for example, a bias error is satisfied, or even, say, this type of L2 error is satisfied. And what does it allow then? It allows for the following construction. If you want to create a multi-level adaptive method, what you derive, essentially the discretizations with, is with a sequence of tolerances. So if you have a reliable single-level adaptive method, the only step that you need to go from there to a multi-level adaptive method is just to create a sequence of tolerances and to say that the first level will be defined by discretizations of my single-level adaptive method, right? So that they reach that accuracy. The next level is, again, refinements on those that achieve the next accuracy constraint, and so forth for all the levels. So you see, now each of the levels does not have a prescribed age. This notion is gone. Each of the realizations may use a completely different mesh that adapts to the characteristics of the omega that you have in mind, right? But still, one will be able to extract the good properties of the variance convergence, right? The mean convergence, and the rates of the explosion of the work with respect to the level. Okay? So what is optimal, at least to show results on the algorithm in this context, is to refine according and to stop according to these simple rules. Essentially, what you do is to compute solutions and error indicators Rn for each time step. Again, the error indicators Rn in the context of this error densities are defined essentially as rho n times delta Tn squared. I mean, and rho n could be the weak error if you're controlling the weak error, or the strong if you're using the strong approximation. That's not important. But again, now this is defining the contribution from time step n in a given realization to the total work. And what we do to stop the discretization is to verify whether the maximum of these guys is or not above this. And this, you see, is the tolerance that we prescribe for the bias constraint, which is what we want to achieve, divided by the expected value of a number of time steps. So this essentially is the mean error that we would like to achieve on each interval. That turns to be optimal, essentially, to equidistribute the error along intervals. One caveat, though, this n is not known a priori, right? Because this is the number of steps that you need to solve. So this has to be found on the fly. But DCS is a constant, and DCR is another constant that are essentially probably independent. So what you have to remember here is that DCS is going to be not the same as this C of refinement. The refinement criterion is a little bit more stringent than the acceptance. So essentially, if you see that you're not going to stop because some of them are going to be larger than that, well, then you are going to refine many more than just those that not satisfy this constraint. Okay. Now, another technical point in this construction is the following: if you have a refinement and has not been accepted, and you mark some intervals in time for refinement, you need to produce essentially the corresponding interpolation values for the delta W's that drive your discretization. And these, not to introduce any biases, have to be consistent with the points that you already sampled. And this is done according to Brownian bridges, right? That is the correct way to do this discretization. So this plot essentially shows that. I mean that for a given level, for example, you use the blue discretization, right? And this entails evaluating W at all those points, but now you need to evaluate W in points in between, and of course they are not going to be linear interpolants of the previous values, but they will differ upon, and this difference is actually given by the Brownian bridges. Okay, so it's just conditional Gaussian sampling. That's nothing more. Okay, any questions? No? Okay, so what was the main idea again? Let the tolerance in the adaptive algorithm define the hierarchy. That's essentially what you have to remember. And this this works in any problem. If you have a sound error density of PDEs or AZEs, you can just use this approach and it will work. Like I said before, adaptivity is useful when you have issues with A or B, or the process itself may have issues with respect to, say, boundaries where it is being, for example, stopped or reflected, that those actually ask for adaptivity. You may have stiffness as well, and this is also nicely treated by adaptive algorithms. So again, if you have a stiff drift, you may choose at least delta t if you don't want to go through this a posteriori global error control. If you just want to drive things by stability, you just may take delta t's to make sure that you remain within the stability region of the method, and that again, if the stiffness is just coming from A, can be done quite easily. Okay, so what is interesting here? Well, the point is the following: when you do a posteriori error estimates, you show things about the discretization being efficient or not, in the sense that the estimate for the error essentially gets close to the error you want to impose. What in this context of error densities you can show actually is you show much more. You can show actually that the algorithm stops, that asymptotically you have normality, asymptotically you have accuracy, and then again, what is asymptotic in this case is when tolerance goes to 0, right? There is no notion of H going to 0 because H is gone, right? So the only parameter that drives the discretization here is the accuracy constraint, and the accuracy is given by toll. So when you look at asymptotics in this context, is when toll goes to 0. And of course, we have kept the confidence level constant in this discussion. We are not letting the confidence go to 1. So asymptotic normality, you also have asymptotic accuracy. That I will just tell you later what this means, but it really means that when tolerance goes to 0, essentially the error is bounded by toll. And the complexity essentially is up to essentially a constant. You get the optimal complexity. So for the Ito stochastic differential equations, there's one discussion that I have not made, and I just put the warning here. It's actually working fine in the theory, but it's not obvious. It's that the discretizations that you get are not adapted. I mean, they're adaptive, but they're not adapted. Adapted means that they're not adapted to the natural filtration of the problem, which is given by the Wiener process. Why? It's because the density, and I have not told you maybe, no. These densities essentially involve variations of the final value with respect to the current value. So essentially, they may need, for example, derivatives with respect to the position xn of g of xt capital var. This quantity is not adapted, right? It's looking to the future from, say, the current point n to final time. So in principle, you can discuss, okay, whether these things are going to converge to the correct solution. They do, but I mean, this is not true for any adaptive method that you can come up with, and one has to be worried. I mean, at least careful about it. Okay, so that's why. So if you do examples here, for example, you have a drift singularity. This is just going to be simple in the sense that the stochasticity is really not relevant. I mean, here we have, say, a deterministic time for the singularity, and the mesh is going to refine automatically around the value of alpha. We are not telling the algorithm that alpha is there, but it does find it. You see the mesh here is refined from the level essentially 10 to the 0 to 10 to the minus 10. just to control the error. Okay. But again, like I told you before, this is a sort of deterministic type of singularity. So in this case, it doesn't pay too much to let delta W to depend on omega. Delta W is non-uniform, but it really doesn't depend on omega. So you can split the construction here in a first phase where you actually find all these meshes that you're going to use in all the levels, and then you just run in the second phase multilevel Monte Carlo, increasing the number of samples that you need on each level until you hit the variance constraint. That is effective. Okay, and actually what you can show is that the cost of the first phase to find actually the optimal discretizations in multilevel Monte Carlo is much cheaper than the actual cost to solve the problem. So that's the gain actually when you have deterministic type of singularities, that you can find a mesh very quickly. Okay, so in this case you see an advantage from uniform to adaptive. You don't see much more of a difference between uniform multilevel Monte Carlo and adaptive multilevel Monte Carlo, because essentially what happens is that this singularity is not strong enough to modify the strong rate. It does modify the weak rate, but if you remember what I said before, the complexity in multilevel Monte Carlo is mainly governed by the strong rate. I mean, there is some dependence to the weak, of course, but in the inequalities that I showed you before with these conversions of the sum, the strong rate was the one that was opposing the work growth, not the weak. Okay, so but if you actually go to stronger singularities, so now we let P actually be beyond 1/2. And of course, you have to make sense that this AZE actually has a unique solution and blah, 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 but it does actually, as long as P, I think, is less than 1 strictly. So you can see here for P equals 0.5, that was the previous example, you don't see much of an advantage between multilevel Monte Carlo uniform and adaptive, but as you start raising the P, you clearly see the advantage between adaptivity and non-adaptivity. And again, I have to tell you one more thing. This has been done using the strong density, not the weak density. So the latest work that we have for adaptivity is actually on the strong. I mean, you use the strong density to rewrite this L2 error, and you now create the levels according to this strong density. That's how this plot is being created. One more thing, okay, the alpha here was uniformly distributed between 1/4 and 3/4, so actually the meshes have to be stochastic, so because the position of the singularity is being just jumping around. Okay, so I told you essentially how to do adaptive multi-level Monte Carlo approximation. Yes, please. Yes, she.
Alpha is independent of W?
Sorry? Alpha is independent of W, that's right. So essentially you set alpha, you run the things. Alpha is independent of W, correct.
Because in the true model, you might imagine that alpha is connected with...
Yes, I mean, this was just a simple example so people can actually reproduce and see what is going on. But yes, I mean, and things can be more complicated because the singularity can, as you're saying, can be coupled with the dynamics. Okay, so it could be that actually the singularity is appearing because of some drift problem, right, with the stiffness, or it could be that X is getting close to a boundary and the boundary has an issue. So you can think of the boundary being penalized, and penalization is drift stiffness, right? So yes, but that will not be able to be written in one line essentially. So yes. At least this motivates what you can gain. Thank you. Okay. Any more questions at this point? I'd like to then summarize what we did on this topic. So I hope the idea of adaptivity in this context that I gave you is quite general. You can use it for any problems you want, essentially, as long as you have a sound single level analysis, if I may say. Okay? The message is that it is better in the context of multi-level to use an analysis that will go towards the L2 error, if possible, right? Drive the analysis of the construction of the levels according to that. Of course, you need the bias error to control the number of levels you're going to use, but at least the distribution of the shape of the meshes should be done according to the strong error. And actually, that can be proved, actually, that it's optimal to do so. You just write a problem that is related to this, but instead of writing this part here, you just write the error density times the integrals of the error density times the delta t's. You just write the whole Lagrangian relaxation, which now will involve finding functions delta t L, say, from L equals 0 to L capital, and then you will see that delta TL is directly expressed in terms of the raw strong, not the raw weak. Only the last level is connected to the raw weak, but all the rest are driven by the raw strong. And therefore, that motivates directly to the use of the strong for adaptivity that we found later, sorry, but I mean, the first works we did was with the weak adaptivity. So how do we do with the time? We split in between, or?
As you like.
Okay, I can just draw the conclusions and it will take 5 minutes. Let me put the conclusions and then. Okay. So as conclusions, I told you again that this way of thinking for multi-level and adaptivity is quite general. You can use it in anywhere you want. You have to be careful though that when you replace the statistical constraint, which means that the statistical error has to be less than 12 with a prescribed probability, computationally, it's much more effective to write that into a variance constraint, and this can be done as long as you have a central limit type of approximation. The central limit does not apply directly in the multi-level Monte Carlo setting because you have sum of independent but not identically distributed random variables, so you have to resort to some Lindenberg-Feller type of result, and you have to verify again this for each of the problems that you work with. So you have to be careful with that. Okay, so let's leave Poisson random measures for the next one. Thank you. 5 minutes?
Yes.
Yeah, okay, 5 minutes. Thank you. So, we are going to discuss another idea for adaptivity in this second context. The second context involves paths that are also random and depend on time. So, but as opposed to the stochastic differential equations that we were given before that were Ito type, these paths actually can be solved exactly. So these paths are given by piecewise constant functions, and the only random thing about them is essentially the time where they jump and which kind of jumps we have them. These processes are very popular. They are Markov processes, of course, and they are used in zillion applications, but let's go a little bit more into them. This is a logarithmic scale. This is time, and here in blue, red, and green are 3 components of this vector that is changing according to time. The numbers that are shown here evolving are the number of species for each of these 3 components. So you can think of 3 populations randomly changing inside of a system according to maybe biological reactions or chemistry reactions, for instance. And even though these green paths do not show it, they are as discontinuous as the blue ones, essentially. Okay? It's just that you have logarithmic scale and you may be fooled by the logarithmic scale. That's it. Okay. So that's a motivational example. This is a gene transcription and translation. You have here in this system the component G that may react given G itself and M that actually may react again and give M and a P, and the P that actually goes into D when it meets itself, right? So you see that they are sort of reaction channels. Essentially, when this thing happens, you know deterministically what is going to happen. The only problem is that the time where this occurs is not going to be prescribed a priori, it's going to be random, right? And let's think of a simple example. Let's think of water, say in a container, and water can be created from hydrogen and oxygen, and it could also dissociate into hydrogen and oxygen. So this is a reversible equation, right? But the way the speed of these reactions actually happen depend, of course, on the temperature. But if you fix the temperature out of this discussion, they depend, for example, on how much hydrogen and oxygen is there. Because if there is no hydrogen, oxygen will never meet hydrogen to create water, right? So the likelihood of these events to happen depend on how dense these components are in the system. Yeah. So and this can be mathematically described. So what we want to do again will be to compute some given output quantity of interest at a given final time up to a certain tolerance, again with high probability. So how to describe the evolution of such a system? I told you before this was an X that lives on a lattice essentially because it's counting. So the components of X essentially describe different species in the system. So we count how much of the species 1 we have, how much of the species 2 we have, and so forth. Okay? So X is taking values on this lattice, right? And evolves according to time and of course omega. Now, we assume that we only have finitely many possible reaction channels, like in the case of water, for example, we may have 3 components. One is describing how much hydrogen, how much oxygen, how much water, right? And we can only have water dissociating into hydrogen and oxygen, and the other 2 meeting to get water. So when this oxygen and hydrogen meet, right, we assume that they can only create water. So there's nothing stochastic about the fact when we know that they meet. The question is when they meet, and this is the stochastic part. Okay, so when this thing happens, right, the J reaction type of in the system happens, the only thing that we have is a change from X, that was the state of the system, into X plus nu J. In the case of this water, for example, when oxygen and hydrogen meet to create water, you have a +1 in the water and the corresponding minuses in the oxygen and the hydrogen. Now, when does this happen is given by the so-called intensity functions for the jumps, or in this context also called propensity functions. These are non-negative functions, AJ, that are evaluated on the state X and give values on R+. So that the probability of having a reaction of type J in an infinitesimal interval that goes from t to t plus dt, given that you have the state X, is essentially AJ of X times dt. Okay? So for instance, if you have no hydrogen in the system, you know that new water is not going to be created, right? So this AJ corresponding to that reaction will be 0 in that interval until that situation changes. So again, we want to compute the expected value of a given quantity for the given observable G, and the applications are everywhere, so I'm not going to stop on that. They have plenty of references, and as well this is not complete, but we just wanted to show a little bit the efforts on this multi-level version. So what is interesting about these systems? First thing, as opposed to the previous discussion that we have, is that exact algorithms are available. What do you mean by exact algorithms in this context? You remember when we sample a la Monte Carlo to approximate quantities of the expected type, we always have statistical error unless the problem is trivial and has no variance, and then we're not discussing anything stochastic, right? So exact in this context means pathwise exact. Essentially that with finite work, you can simulate a process that has the correct law. Okay, so there is no bias error. So you can do unbiased simulation with O1 cost, which means that already you have, the beautiful, regime that we discussed before that was told to the -2, right? I mean, the cost is told to the -2 comes from the number of samples in Monte Carlo, and then O1 to solve for each path in the mean. Yeah. Okay. So the whole discussion here is about constants. So you do variance reduction in order to reduce the constant in front of the 10 to the minus 2. That's the whole point in this context, as opposed to the other case where we actually can push the complexity from 10 to the minus 2 log square times 10 to the minus, into 10 to the minus 2. Here it goes from 10 to the minus 2 into 10 to the minus 2. Okay? And still you can get impressive gains. So constants matter, that's what I'm trying to tell you. Okay, so then if you have an exact algorithm, why are you going to introduce an inexact one, right? Well, because of two things. Because the statistical error is already there, right? So having a bias that is 0 in the presence of a statistical error may not be optimal, because the cost of simulating such exact path may be a lot, right? So introducing a path that is a little bit cheaper and has some bias, and the bias is smaller than the statistical error, will not change things dramatically from the error point of view, but it will do it from the work, right? So it is actually good. It is a good idea to actually introduce bias in an unbiased simulation, right? Good. So what is the problem then here is that essentially the cost comes from all these events that are happening in the system. So if you actually have a lot of molecules in a big reactor, right, you can think that there are a lot of reactions happening, and if you have to track all of them to do this exact simulation, the cost is going to be horrible. Okay? How horrible? Well, essentially these interarrival times between jumps are exponentially distributed with intensity that is the sum of all the AJs in the system, and this can be a large number depending on the system. Okay? So, as opposed to that, then one would like to do approximate time stepping that is cheaper but introduces a bias. This has been done pretty much from the tau leap, that is a forward Euler method, to more refined versions of it. And you have drawbacks, of course. First is you're going to introduce a time discretization error that you didn't have, right? And two, you may have non-intuitive, at least qualitatively wrong type of behavior. Essentially, if you go back to the discussion that we had at the beginning, our process is actually counting molecules of different types in a system. These are not going to be negative, right? These are not, if you're doing the proper thing, the true trajectories will never cross 0. But if you do these sort of approximate algorithms with a non-zero probability, you may cross these things, and you may want to avoid these events because they have an issue on the accuracy, on the global accuracy that you can get. Okay, so there are ways to deal with this. For example, the pre-leap is just to adjust adaptively the time step in order to control the one-step exit probability. But we would like to always relate things with respect to the goal, which is to relate all type of errors that we have in this approximation with respect to the goal, which is the expected value of g of xt capital. So what we did in this line of adaptivity was to first create a single-level hybrid algorithm that at each time step adaptively switches between the exact path simulation and this tau leap sort of Euler in order to do what? To minimize the computational work. So why is this somehow needed? When you're close to this 0 level that you don't want to cross somehow, the tau leap, which is the approximate forward Euler type of discretization, that does have a cost that is not being reduced somehow, okay? So you're not gaining too much from using it. But the exact simulation essentially has a cost that I told you was essentially going up with the number of particles in the system. If you're going to get closer and closer to 0, right, that cost actually gets smaller. So close to boundaries, in this respect, the exact simulation is advantageous because it doesn't introduce bias and it's cost to do because the interarrival times are large, relatively large at least. Okay, so this can be quantified, and a rule that switches between these two things can be done. So again, this is adaptivity, but now not adaptivity just with respect to time, but between methods, right? So you're combining two methods, one that has sort of infinite accuracy or infinite order with respect to time discretization, and the other that has order 1, which is essentially coming from Euler. Okay, so that was one thing. The other thing is that this idea can be generalized into multi-level Monte Carlo algorithms for error control, again. And not only that, it's like you can do this according to the different channels. So I told you before that when you introduce this, there are different J channels, right? And with respect to these J's, what matters really is the propensity. If the propensity is sort of large, you're taking a lot of events over a unit time step. If the propensity is slow, these things fire not often. So if you can actually split among the reactions, do a time splitting method, and essentially treat some of the reactions with the approximate method and some of the reactions with the exact method. This can be done as well, even in the context of multi-level. And again, all this, what is going on here is that you're introducing biases and approximations that have much less cost when compared to the unbiased algorithm. This is why this gets useful. Okay. So how do we go about it? I mean, to motivate the different methods. The whole thing can be written through this Kurt's random time representation as a counting. I mean, as a counting algorithm. Essentially, the number of species that you will have at time t, essentially is the number of species you have at time 0, right? Changed by what? Changed by the number of times the J's reaction occurred. And the number of times the J's reaction occurred is described here by a Poisson process whose intensity is non-trivial. It's just the integral from 0 to t of aj, the propensity of the reaction j. This is, again, a non-negative function, and this is just a random time change on a given unitary Poisson process. Okay, so this is a natural number that goes from 0 to whatever, and this is just the vector that introduces the changes according to that reaction. Is that clear? So it's just bookkeeping, you see? And if this A would not depend on X, this would be trivial to simulate, right? You will just change accordingly the time in a unitary Poisson process and know exactly when the jumps are going to occur in your system, and that's it. Okay, so to simplify this, when you want to do approximations, you just do an Euler method. Essentially, you freeze the value of A at the left point and approximate this increment by a Poisson random variable with intensity Aj times delta t, if you wish. And the first time they wrote it, they put tau here, and this is why they call it the tau leap method. Okay, so first problem that you see here from this approximation point of view is to find tau so that you're not going to cross these important boundaries with a given probability. Delta is given. So this tau will depend on x and delta, and this will prevent you from jumping according to this inequality. What we did actually to use some large deviation Chernoff type of bound to actually come with a computable formula that one can use to ensure this inequality. And then from this delta t, we can actually discuss whether it is worth taking the approximate step or the exact one. Yeah. So, and then one step further is to go into a global probability of going out, because remember, this discussion that I just made was based on one step. Essentially, if you're here, how you have to take delta t, so the probability of exiting in this time is below a certain value. Now, what you really want is the probability of the whole path going out or not going out, right? So you have to link the one-step probability to the whole path probabilities, and then link these quantities into the effect of the global error that we really want to compute and approximate. So this is the first step that is good, because I mean, in principle, the probability of going out for a path, if things are going to be done correctly, it's a rare event. So you want to, instead of sampling that rare event, you want to compute quantities that are sort of easy to deal with, and this approach does it actually. Okay, and like I told you before, then one can write a multilevel Monte Carlo based on these type of paths, right? Find the m's and find the L. So you control the exit type of error, essentially that is related to the indicator function of the path going out. and that will produce an O1 error. So essentially, that's why essentially you have to compute to control this via the exit probability. Then the weak error, that is more or less what we have discussed before with the diffusions, and then the statistical error that doesn't change from the discussion that I made before. So the issues addressed here is that you have to do things correctly to simulate coupled pairs that have the right law and are correlated in the right way. And of course, being able to accurately estimate the different quantities in the multi-level construction. This is particularly non-standard here from respect to the diffusions that I described before, for the following reason. The paths, right, they're taking values on a lattice. So when things are going to converge, right, I mean, as you discretize the delta t, or you increase the L if you wish, the paths are going to be closer and closer. But you know, in diffusions, closer and closer may mean, you know, you're in a continuous space, so they may mean actually getting closer and closer. But here you're in a lattice. So what does it mean to get close in a lattice? Either you're far or you're there. So actually, closer in this setting, it means that the probability of going far is going to 0, right? And the probability of being equal is getting larger and larger. What's the problem with that? The problem is that this creates immediately high kurtosis. And high kurtosis is bad news in the multilevel Monte Carlo context because it makes the estimate of variances difficult. Okay? So one thing that appears here naturally, as opposed to the diffusion case that I discussed before, is you have to work a little bit further to estimate the right variances in your system. Remember, the m's are driven by the variances, so you need good estimates of these quantities, otherwise your estimates on the m's are wrong, and if the estimates of the m's are wrong, bye-bye Monte Carlo, right? Okay, so that's important from the practical perspective.
It is linked to delta, L, the index L.
Little l, yes.
It is linked to delta that you use to bound the probability of AC.
Yes, everything goes there. So everything goes into there. I mean, each level in principle here contains a delta TL, but contains also a delta L, because remember there was this probability of going out, right? So you may prescribe this delta L as a function of the L, and also a delta L maximum per level. So this thing goes as before, like delta T0 divided by 2 to the L, for example. But this doesn't go that fast. This is chosen in a different way. So these two things combine to give the method. Is that clear? So these two are varying. All right?
Thank you.
Good. Thank you. Okay. So this is an example, the example that I showed you at the beginning. And here you see that from the exact method, essentially, which is SSA, the error bound, right, versus the tolerance, essentially, goes like 12 to the minus 2. So essentially, this is the complexity that we have. And if you use this hybrid multi-level, you can still keep the same complexity, and what you gain is a constant, but the constant can be substantial. All right? In this case, it's 10 times faster. And this is actually the usual plot that you would see in our papers. It's the control of the weak error. So what the user gives in this context is a tolerance, but he also prescribes the confidence level. So in this case, the confidence level was prescribed to be 5%. So when you do your simulations, essentially you expect to see around 5% of them going above the prescribed tolerance. So you see here, the tolerance is getting lower, and the corresponding sample error for the different runs of the multilevel Monte Carlo distribute like this, and then essentially these numbers here are the percentage of those above the bound. Okay? So you change the quantity here, these exceedance values should change as well. All right? So, okay, so you can actually have Depending on the problem, different type of gains. I'm not going to discuss this too much, but you can go above 10, of course. I mean, you can get 10 to the 4, things like that. But the plots look like this always, right? You're improving the constant. You're not improving the rate. The rate was optimal to begin with, right? So it is actually paying to introduce a bias approximation with respect to the unbiased method. Okay, and here's an example of a reaction splitting method where you actually do this differently in the different reactions to get even farther. Okay, so this is, I think that's it. So summarizing here, this is a different type of idea for multi-level adaptive, right? You're switching between methods. Okay, you can also do the delta T adaptive as well, but here you're switching between methods. And you're going from an unbiased method into a biased method to improve the constant in the complexity. All right? Any questions? Okay. Okay, so now we discuss discretization from another point of view. We're going back to uniform discretization, but now we ask a different question. We say, we have been driving our discretizations with this type of geometric type of refinements, right? I mean, you get an initial discretization parameter, then you divide it by a given number, then you divide it again by the same number, and so forth. Okay, this is natural within, again, numerical discretizations, right? You try with a mesh, then you subdivide it, you try with another mesh. Is that optimal? Is that optimal? That's a natural question to ask, right? I mean, should we choose the HLs or the delta TLs like this, or should we not? Answer, no, it's not optimal. Okay? So, with some assumptions, you can show that this is not optimal. This is the work we did in this optimization of various hierarchies for Mathématiques Monte Carlo. And this other work that is here, this continuation of Mathématiques Monte Carlo, addresses this problem, right? That these variances that you need actually to drive and get the optimal M's are not known a priori and somehow have to be found on the fly, right? So you need to create an algorithm that not only is adapting the M's, but is trying to find these parameters that are needed to find the M's, okay? So that's what the continuation is doing, and this is implemented in the lecture, in this code MIMC-lib, this library MIMC-lib. Okay, so let's go to the assumptions then to focus. So what do we have here? We have a multi-level Monte Carlo method as before, but now the levels, GLs, are going to be driven by these HL the parameters of discretization, and we do not say that they are geometrically distributed a priori. Okay, so we're going to let them vary. So we're going to take L capital plus one of those, and we are going to assume that essentially the weak rate is algebraically convergent. The strong rate, again, is algebraically convergent, and the work per sample is algebraically divergent, as in the linear PDE that we have before. And then what we have to find are not just the M's, but also the H's. Okay? Is that clear? So as you know, the constants and the Q's here will depend on the problem and the solver, as we discussed before. And these are just a couple of examples, right? In Euler-Maruyama, you have Q equal Q1, Q2 equals 1. And if you have the other PDE example, we already discussed that the Q1 was 2 and the Q2 was 4. Gamma, again, is defined by the solver, and is obvious in SE with Euler-Maruyama, it's just 1. So I don't stop into that. I just try to show you that these things can be found. And if you have no theory at all, right, if you're desperate, you can just try to fit something to the convergence that you see, right? Or the explosion in the solver. So you can actually measure things as well. So two useful quantities here is the quotient between the strong convergence and the explosion of the work, that is chi, and the eta is the quotient between the weak convergence rate and the explosion of the work. Of course, the best case for multi-level Monte Carlo is when chi is larger than 1. The limit case is chi is equal 1, and the sort of algebraic improvement with respect to Monte Carlo is chi less than 1. All right? And again, you see that if you change the solver, you may change from chi greater than 1 into chi less than 1 as I described here. In the PDE example, if you use an iterative solver, you get 1.34, and if you go into the direct solver, you get 0.89 already. So you can influence the conversion rate of multi-level just by changing the solver like that. Okay, so the optimization, how does it look? Well, it looks like this work, that was the work that we discussed before, subject to this constraint. This is a bias constraint, less than this fraction of the tolerance, and this is the statistical constraint, which means that the total variance, right, is less than theta times tau divided by C alpha, and C alpha again is the confidence constant that is coming from the user, essentially when he imposes the confidence level alpha. Okay, so the good news is that you can solve this problem, and of course you can even verify the normality, how far you are or how close you are when you do actual computations. And here's the result somehow for k equals 1. You actually have, is a case where you actually have geometric discretizations. But I have to warn you, these geometric discretizations, you see HL is somehow beta to the L capital minus L, so it's a subdivision like we discussed before. This doesn't depend on the levels, but it depends on the toll. So it's not your usual geometric discretization that you would think of. Okay, and the beta actually is not 2 or 3. I mean, it's something that may even have an influence on toll. Okay, so the spacing between the levels is non-trivial either. All right? This is one more thing that is interesting here. The optimal choice of the splitting parameter, which is the fraction that you devote to the bias versus the fraction that you devote to the statistical error, actually goes to 0, goes to, oh, come on, goes to, I mean, the fraction of the bias goes to 0 as toll goes to 0. Yes, that's right. So essentially, if you see here, theta is the fraction that you give to the statistical error and 1 minus theta to the bias. So theta essentially goes to 1. Why? Because eta is fixed and L goes to infinity. So this theta is going to 1. All right? So asymptotically, you're putting most of your error, your error allowance to the statistical error, not to the bias. And of course, the level behaves like log toll and with this constant. But for non chi equals 1, things become less simple. You can still find relations on the theta, and you can find bounds on the number of levels with respect to the different parameters as this shows. Okay? Nothing really changes from the classical results in terms of exponents, but you can identify how the input constants affect the actual complexity in the actual constants. So you can play tricks to reduce these constants, knowing that they exist and the shape they have. Okay? So the shape they have in these constants in the different cases are like this. So you can actually see that in some of them, for example, the variance of the level 0 plays a role, but in some others they don't. So here in this setting, if you're here, you may get an advantage by doing a special trick for level 0, say, whereas in the other cases you may not. Okay? So, like I said, the exponents are the same as you have in the classical theory, but now you identify the constants as well, and you identify how you have to space the levels too. And that is more or less the discussion that I have here. These are not going to be necessarily nested because you have this beta that behave in a strange way, and the H0 also, the first mesh, also behaves in an interesting fashion too. Here's a discussion on the continuation multilevel Monte Carlo. And again, the plots always look, I mean, like I discussed before. You have a direct solver here and an iterative solver. You have the prescribed error, and here's it versus the tolerance. And you're checking essentially that when you run over and over and over the multilevel approximation, you get a fraction of those that go above in accordance to more or less the confidence level that you prescribe. Now, coming back to this question of finding the variances and other relevant parameters to do optimization, in the continuation multilevel Monte Carlo, what we do is to solve a sequence of problems until you hit the problem that you want. So essentially, what happens? We know that in the best possible case, the explosion of the work in Multilevel Monte Carlo is 12 to the minus 2, right? Best possible case. It could be even worse, and you can have a log torque here. But I mean, the worst is like this. So if you actually solve now a sequence of problems where you first begin with told 0, say, and then you go times told 0 divided by a certain fraction, right? Call it f, and then keep going, right? Until you hit the actual tolerance you want, you can sum these works here, and you can get a choice on this fraction so that the actual sum of these sort of preliminary works does not create a huge overhead on the last one that you want to solve. That's the first idea. And then what happens here? That when you start solving these sort of auxiliary problems, you start learning the constants that you need, okay? So somehow by creating these fractions, you do not overshadow the actual work that you want to do optimally, but you start sort of uncovering a veil over the variances that you need and the other things that you may need to find the optimal ends. That's essentially what is behind the continuation Multilevel Monte Carlo. It's sort of, you know, a motopate with respect to toll type of idea. Not really complicated, but it turns to work quite nicely. Of course, on top of that, there are tricks to actually improve a little bit the variance estimates on the deeper levels, right? I mean, what happens statistically is that in the coarse levels, you have a lot of samples, just by construction, right? I mean, Multilevel Monte Carlo produces a lot of samples in coarse levels and very few in the deep ones. So, but the deep ones are the really costly ones. So if you make a mistake in the variance there, you make a mistake on the M, and things go really rotten. So to get better hold on the deep levels, you actually do some kind of Bayesian type of estimate, where you use as a prior model an extrapolation that is coming out of the coarse levels, and you enrich it with the few samples that you have from the deep levels. That's what is behind too. So it's not just one idea, but I mean, I'm just telling you the couple that I consider most relevant. Okay, so the good news again is that if you do all this sort of little learning process, the complexity that you get is not much of an overhead with respect to the optimal line here. That will mean that for this sort of pink magenta type of a curve, you are just writing the cost that you would incur if you would know all these nice constants beforehand with respect to finding them on the fly. Okay, so it's not too much that you have to pay, really. Okay, so that's with respect to the optimal split in theta, and it's not really much relevant. So what is the second part of conclusions? We didn't discuss much of normality, but we have a result on using the Lindenberg-Feller in this context. Better splitting between bias and statistical error can improve the work a little bit, and this continuation Multilevel Monte Carlo tries to provide a more stable algorithm that allows you to find the constants in between. Geometric hierarchies are nearly optimal, but they are not the geometric hierarchies that you are used to work with. Okay, they come from this optimization. They have specific values that may depend on toll as well. Okay. Okay. So for Ito SEEs, I included in the slide some assumptions and some results with respect to the densities that I don't have time to comment on, but I'm going to share the slide. So if you have questions, you can come to me. Again, I emphasize here that these phi's actually depend on derivatives of the final solution with respect to initial conditions. So this is what really makes the method non-adapted to the natural filtration. Okay, so let's see, this is multi-level in that context. This is what I meant by strong convergence and the accuracy result. This is what I meant by the work optimality result. And I include a little bit more in terms of the complexity. But, okay, CLT, 2. Okay, so last thing before I run out of time, a little bit of adaptivity with respect to M, and I just touch upon the classical expected value computation using just Monte Carlo, just to close it up. So what's the point here? You want to compute the expected value of X using IID sample averages, and you want to prescribe again this delta, which is the confidence level, and you want to prescribe also the toll. Okay? So what is the point here? The point is that usually you do this approximation based on the central limit theorem. That rule, that will be a rule of the following type. Essentially, you are going to prescribe toll and you are going to prescribe delta, and then a number of samples M will come out. May not be so reliable when you have X that has low decaying densities, essentially heavy tails. So for that reason, we provided a rule that it's a little bit more robust and essentially combines the central limit type of approximation with other type of bounds. And let me walk you through a little bit before I finish. I have 10 minutes, right?
I even have 5 minutes.
Yes, okay. So this is going to be a little bit intense then. Okay, so this is a general stopping rule, right? Based on the samples, you're going to estimate the probability of failure, and based on that, we are going to accept or not. So the probability of failure actually is the probability of your approximation not being close enough to toll with the prescribed probability. So this event of failure having a value larger than delta, essentially. So again, as we described with the central limit theorem before, the use on the variance constraint, you can actually, if you believe that your sample average, your sample variance is actually accurate enough, you put a rule of the central limit type, substituting sigma here, which is the true standard deviation, by its approximation. And if this actually is accepted, then you stop and you give your approximation. This may have issues. Okay, so consider the following Pareto distribution. The density is decaying like x to the minus 4.1, right, for x larger than 1. And you see here the behavior of this quotient. This quotient is the probability of the actual failure versus delta, the one that you wanted to impose. So if this quotient is larger than 1, this is bad news. This quotient is less than 1 or equal than 1, it's okay. So you see here tolerance versus delta, right? So here it's like having more and more confidence in your computation, and here is more and more accuracy as you go to the left, right? So as you let tolerance go to 0, essentially for delta fixed, things are going to be fine. But in the regime where delta is, say, a few percent, and sorry, when toll is few percent and delta is sort of stringent, and that's natural for engineering computations, this is not going to be nice. It's going to be actually in the red, and it's not going to give you the prescribed tolerance. So there are many results in the literature where you fix the delta and you let toll go to 0. What I claim is that essentially those results overlook this regime, which is important in the applications. Okay, so the whole point here is to penalize this fact, because we really don't believe sometimes that we have such an accurate estimation of the variance. To uncover this, what we do essentially is to use various n type of bounds that are essentially sort of better control rates on the approximation in the central limit theorem, and combining those with a sort of Edgeworth type of expansion, which is something that you would use when you have full confidence that the tails are going fast, essentially, to 0, then you get sort of an improved rule. And when you go above this rule, you actually see in this example that you can achieve the right prescribed failure rate with almost no change you see in the computational cost. And the cost here is just determined in terms of samples, because we are working with just Monte Carlo in this context. Okay? And this can be done also for another kind of not so nicely behaving random variable. And you see again that for small delta and relatively few percent tall, this is a bad case. But you can fix it using this other algorithm and without incurring too much in an increase of the work. And finally, this is an example where we actually expect the usual approach of central limit theorem to work nicely, and it does actually. The work here is such that the failure probability is below the delta, but this algorithm also achieves that without an increase, a sensible increase in the work. Okay, so in the nice cases this behaves well. In the worst cases, or the bad sort of cases, this will have better control on what is going on. Okay, so that's a summary, and I think I get to my end. That's remarkable, actually. So thank you.
Are there any questions or comments?
Yes, Emmanuel.
So I would be interested to know if we could apply this criterion, for example, in the case where X is related to a rare event. So that is a Bernoulli random variable, typically, which is 1 and 0, but 1 with very small probability. So what?
That's not the case we looked into.
Okay.
I think that needs a measure change. I don't think one can apply it directly
but
here.
Just using simple averaging of your output. So how robust is the criterion to...
I mean, what I'm saying is that it can be used, but provided that first you do a measure change. If you don't do a measure change, all estimates are going to be wrong, right?
Oh, you mean wrong, inaccurate, in fact?
Absolutely, and
Okay.
the whole thing is completely unreliable, right? So red event asks for a measure change to start with, and then if the measure change is sound, the importance sampling is sound, then you can use things like this. But I wouldn't recommend use this in a red event without looking into an importance sampling algorithm first. It can be combined with this, that's what I'm saying, but I wouldn't recommend it to use it without the importance sampling step first.
Can I have a second question, perhaps, if I
Because again, that regime is different, right? I mean, that regime is like, for example, 0, 1 with a very tiny probability of achieving 1, and here is like unbounded, right? And you can get unbounded variables, right, with a certain probability, and this decay is not that fast, so you can achieve them with the probability that is not so negligible, and this is what gives you trouble in the estimation of the variances. It's not the same regime as the.
Have you looked in the direction of concentration of measure inequalities, like we know?
That's also not applicable here in the sense that for concentration of measures, at least if you use classical large deviations, you need exponential moments. These guys do not have any, right? I mean, we use them in the Chernow for the tau leap, but here you don't have any exponential moments. So maybe if you have a concentration, it's too little.
Maybe a short comment. Maybe the applicability of your method is connected with a kind of ratio between the expectation and the variance. You see, because the case of rare events is that 1 over square root of p goes to infinity when p goes to 0, something like that. The relative value of the expectation.
Yes, but I mean that's also what defines the regime of red events, right?
Yeah.
But in this case again, I emphasize that is the tail that is creating the issue, and we create sort of something that works more or less uniformly with respect to that, and does not address at all the question of the red event. The red event should be addressed in a complementary way. At least it's my humble opinion.
Other questions? Yes?
have you looked, or is there any chance to extend this framework to the case of piecewise adaptivity? I'm thinking of SPD, where you would like to have a discretization that has some local adaptation in space. Pathwise.
Okay, but this is not about this last part, it's the previous part.
Yes,
No,
well,
okay.
in general.
Okay. This is about the, what, again? The adaptivity with respect to... Pathwise, okay. So what we discussed was pathwise, but in time.
Yeah, but the time step is fixed.
No.
Independent of the...
No. The time step is delta t of t and omega. Delta t is fully stochastic. So it can adapt to features that come with omega, pathwise. So yeah, that's actually the most general, but you only use it if you're obliged to. That's my advice, that if you can use, for example, deterministic type of activity, that is cheaper. But you need some a priori information about the problem that you're solving, right?
Okay, thank you. Is there any further questions? If not, so let's thank again the speaker.
Thank you. Thank you. Merci.